This lecture is going to describe a brief introduction to lipids. Okay, so this part is the chapter 2 part on lipids. And I think it's a nice starting point. So lipids, first of all, are often categorized as fats. Hopefully we clear that up in this lecture. So lipids and fats, and really waxes too. These are molecules with low aqueous solubility. Aqueous or H2O solubility, rather they dissolve in organic solvent many times. Okay, that's a pretty cool property of a biomolecule. I mean, I know we've probably heard the term fats and waxes and all that stuff, but just to kind of think through, there's just such an unusual kind of characteristic of a molecule that shows up in biology. Okay, so let's look at a few examples of these. So we have waxes to start. Waxes are mostly esters with long hydrocarbon tails. On either side. Okay, so if we look at an ester, we have R, OR dot, or prime, excuse me. So these are going to be, these R groups are going to be super long alkyl chains on either side. Okay, and they're so long that oftentimes we see the melting point of these start to creep into ambient temperatures, and so it then, or below ambient temperatures, I guess, above ambient temperatures. Yeah, above ambient temperature, sorry. And so these are solid at room temperature, but they're kind of waxy because they're difficult to pack into a uniform crystal lattice. Okay, so those are waxes. It looks like I need some pages, just a second here. Okay, that should do it. So those are waxes. Let's move into the next type, and that'll be phospholipids. Most of the lipids and fats and waxes that we're going to be talking about are esters, just with different kind of groups attached to either end of the ester. Here, these are esters of phosphonic acid, or phosphoric acid, excuse me. Okay, so phosphoric acid is H3PO4. So this is phosphoric acid, and then with that in mind, phosphate is when we have a conjugate base of phosphoric acid. We could have, in this case, we've got the, all three of the oxygens are kind of negatively charged, but we could have the H2 phosphate, the H1 phosphate, that sort of thing, where we've got H plus is countering any one of these negative charges. Okay, so this is phosphate, the conjugate base of phosphoric acid, after having lost all of the hydrogen atoms. And what we can do is we can actually let this replace the acyl group, or replaces the ester acyl group in a typical lipid. Okay, so an example would be, let's say we've got our phosphoric acid, but we've got this strange kind of 2 carbon to a nitrogen with 3 methyl groups, an O minus going this way, and then an O into a few other esters. Sorry, this is just, I just want to make sure I don't lose any atoms here. Anyway, so this is phosphatidyl choline. It's interesting because it's got a it's got I think this is, gosh, is this choline? Gosh, that's got a common name. I'm going to Google that in just a second. But what I want to highlight here that you guys can write down while I'm Googling that is that this molecule is glycerol. Has a glycerol unit, which I'm going to highlight in green. Glycerol is a good molecule to kind of strap into your memory, like just one of those molecules you should. It's kind of like glycine. It's so fundamental that it would be nice if everybody just held on to that structure and associated it with that name for forever. Glycerol is a super interesting molecule because it looks a lot like ethylene glycol, which is obviously super bad because it crystallizes in our brain. But what's cool about glycerol is that even though it looks like that, and this is indeed a choline unit. Okay, got that taken care of. So even though glycerol looks like ethylene glycol, it's actually safe to use and handle, and it's a metabolic byproduct in many pathways. You can feed it to bugs, and it can inadvertently kind of get things to grow and sustain life to a certain degree, kind of. In fact, people add it to solutions, stock solutions of biological material that they hope to store at minus like 80 degrees for long-term storage. If you add it there, if you add it to an aqueous solution, it prevents, to a certain percentage, it prevents ice crystal formation, which can really kind of harm the systems that you're trying to protect with the cryogenic conditions. I'm going to continue to kind of highlight glycerol here. So glycerol, this it looks like 1,2,3 trihydroxy propane or something like that. Propane trial, 1,2,3 propane trial. Anyway, glycerol is the name everybody calls it. So this is a phospholipid. It's a lipid with some ester groups built up upon phosphoric acid. And this is, because it has a glycerol unit, this is a glycerol phospholipid. So it's really common, or it's really complicated words, but they all kind of just build on the various structural units that are present in our complicated esters. So this is a phospholipid built up using glycerol. And so glycerol is just such a common building block for a lot of the fats and lipids and waxes that we see in biology. So like I said, it's important to know that structure. But let's get into a huge class, and this is the Triacealglycerides. These are our fats that we typically kind of associate with when we think about fats. So these are when I say animal fats, I mean animal fats and vegetable oils. Oil is really supposed to be just some substance that's built up with carbon, some organic molecule that happens to be liquid at room temperature. So these are liquids that are mostly these are fats, just like animal fats, but they happen to have some structural defects that cause them to be liquid. And we know that these structural defects actually really help in nutrition. Okay, so triacylglycerides are where we take glycerol and we do 3 esterifications. And you could do these in a number of ways. You could think about them kind of like an acid chloride reacting with an alcohol, or you could have like a Fischer esterification like reaction. There's a few ways to kind of think about it. And the R groups could all be the same. They could all be different. Enzymes seem to tackle this for the biosynthesis, and we'll look at that in an upcoming lecture. But triaceal, that means 3 acyl groups. And these are our esters. And then if we have glycerides, that means an ester, multiple esters in many cases, built from glycerol being the alcohol. Okay, so we see that here where glycerol is the alcohol, that 1,2,3 propane triol is the alcohol, and it's reacting with our carboxylic acids by some pathway to give rise to the ester. Okay, and we saw previously we had a glycerol unit used in a phospholipid. Sorry if I can get it up there. I had that phosphatidylcholine, where two of the alcohols are just simple acetyl esters, and the other one has a phosphorus ester with that choline group attached to it. So there's phosphatidylcholine. You can kind of see where all these names come together. Now you could replace glycerol with a different kind of building block by which you can build your three kind of carboxylic acid derivatives. And a common one is, and I think it's, this molecule is, so these are Triaceal lipids built from, I'm going to write it here, sphingosine. And I'm going to check that just to make sure. But we have some C13 carbon tail attached to an alkene. Now we have some chirality we need to be aware of. But this is going to use a nitrogen and 2 alcohols as opposed to 3 alcohols to get your, yes, and this is indeed sphingosine, to get to your triaceal group. So we have esters that could form here, here, and here. And I guess if it's a nitrogen, it's an amide. So the red are places an acyl group can react. So these are places that an acyl group can react. So anyway, that can replace glycerol and provide 3 places where we can see, 2 places where we can see ester formation and then an amide formation. Gives rise to new and diverse types of lipids. It's a little bit specialized, but you see the name come up. So I just wanted to say that if it's sphingomyelin, these are triaceal lipids built from sphingosine instead of glycerol. Okay, let's talk about fatty acids briefly. So fatty acids are the carboxylic acids resulting from hydrolysis of triacylglycerides. Okay. So, I mean, it's just like a carboxylic acid, but the thing to emphasize here is this R group is long because it's from a triacylglyceride. We've looked at these in various contexts. These are kind of early soaps because people could inadvertently do, people in kind of much ancient societies long ago, when there were some sort of human sacrifice or some sort of approach to decomposing bodies, people used lye, which is a strong base. It hydrolyzed. It does a lot of things to a human body to make it go away and wash away. One of the things it does is hydrolyze the triacylglycerides present in the body down to, and this could be animals too. I don't think that helps anything. And that could, so the hydrolysis released fatty acids, which are a good detergent, especially when deprotonated, which is lye is just super concentrated base. So the fatty acids that were released were in the water, and they found that if they did their laundry in streams downstream of where they sort of did, I think it was some human sacrifices, but any method of decomposing a living tissue, they found their clothes were cleaner, and that's because the decomposed triacealglycerides down to the fatty acids as the conjugate base were really good cleaning agents for soaking up dirt, grime, that sort of thing through micelle formation. We've taken a few tests on this in Organic 1 and 2, so I won't go through it, but just a reminder, that's what we're using, those fatty acids, to do that job. Okay, so moving away from fat, from kind of the typical fats, other lipids are terpenoids, steroids. So these are kind of, call these miscellaneous lipids. So terpenoids, steroids, and icosanoids. So these are typically signaling or secondary metabolite structures. That is, you're not going to see these too much as like a structural feature like you do with animal fats and that sort of thing, where they form like critical aspects of, like the phospholipid bilayer is takes advantage of some of the structures we talked about previously. Here, these are molecules that are in either are used for other purposes like signaling, like hormones and steroids. These are signaling things. Icosanoids fall into that category too, or secondary metabolites, which are kind of sometimes defense mechanisms for survival. These are natural products that we study. So let's get into terpenes really quick. So terpenoids are also called terpenes. Okay, these have a huge structural diversity. And there's some nice examples in the book, but what I want to emphasize is that these are built up from terpene, which is this thing I always envision. I don't know if it's the double bonds, but I always envision it kind of like a horse with front legs and back legs and a head or something like that. Hey, if you don't like it, no worries. It's not a good analogy. So these are built up from terpene to make polyterpenes. So polyterpenes are where we kind of do a diene polymerization, and you get to something that looks like this. Put our little N down there. Diene, come on. Diene polymerization. And you can kind of see the diene features here. He's dying. Okay, better get that out of here because we want to focus on terpenes and that sort of thing. Okay, so these are made through diene polymerization. The usual biochemical starting material is this diphosphate molecule. I can go ahead and draw that out. But you get two circles, P's, and then our terpene framework is right here. So there are the terpene C atoms. And then this other group is just a good leaving group. Okay, so those are terpenes. There's a huge amount of structural diversity. So sorry for not providing a specific example, but I don't think that's the helpful piece right now. Instead, I think it's important to just look at how these things are formed, which is through that terpene starting material. Okay, next we're going to look at steroids. So steroids have a, first of all, they're just very important in signaling. They're big, They're bulky, they're structurally complex, but they do have a regular pattern about the structure, which includes 4 rings. And we call those rings A, B, C, and D. And it turns out that because they start with somewhat common synthetic precursors, some of the stereocenters are actually fairly regular. So you go like 3 6-membered rings in this arrangement, so they kind of form at an angle. You go over and up slightly, and then that connects to a 5-membered ring. We'll look at the biosynthesis in an upcoming lecture, but then we have usually a methyl group up, up, and up. And then we go hydrogens alternating between down, up, down. I think I got everything. So those are the usual stereocenters, but then this is the A ring, the B ring, the C ring, and the D ring of our steroid. Now, furthermore, I want to emphasize this lower left portion. This is usually oxidized. Okay, so these are very important for signaling and hormones and that sort of thing. And so we're going to see those participate. I mean, we're going to look at the biosynthesis of those in this unit. It's fairly common and actually makes the complicated molecule look a little bit less unwieldy. So the next one is icosanoids. So it's interesting that we included these. They're hugely important, but these are molecules derived from molecules derived from arachidonic acid. And so let's draw arachidonic acid at least once. So the way we draw it is we start over here, and this is C10. And the issue is we've got a few Z double bonds to consider. So we've figured out a way to draw this and take advantage of its inherent symmetry. And then we go 4, 3, 2, 1. Oh, 1's right there. Okay. So there's carbon 1 of arachidonic acid. Let's count off. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, got that down. And now we're going to go over to carbon 20 now. So this should be 16, 17, 18, 19, 20. So arachidonic acid is a C20 polyunsaturated acid. And this molecule builds up several types of molecules called icosanoids. And these are also signaling molecules. They are critical. I mean, signaling, and also they're very functional. They do a lot for us to help us understand important processes that, or not understand, but like really regulate super important processes. In particular, they control blood pressure, blood clotting, and inflammation. So as you can imagine, as we move into, as cancer research moves into understanding things like metastasis and angiogenesis, which is like, I think, the formation of blood vessels within cancerous tumor tissues and that sort of thing. So angiogenesis and its relationship to inflammation and how cancer spreads through metastasis, understanding the role of icosanoids in all of these processes becomes hugely important. Okay, so that's a brief glimpse into the types of molecules we'll see as we study lipids, fats, waxes, all that stuff. So we'll stop here and we'll move into the actual biochemical processes, which are covered in chapter 3 in upcoming lectures.